Hi, my name is Darsh, and I'm a senior math major at UT Arlington, and I'm presenting a novel mathematical model of Oropuche virus transmission dynamics, and this is work I did through the Math for Human Health RTG at UTA. Oropuche virus is a vector-borne disease from the Amazon basin, and there's a current outbreak that's caused more than 10,000 confirmed cases just in the Americas. It's theorized that the disease circulates in two distinct cycles, a sylvatic or a forest cycle, and an urban cycle. And it's also predicted that climate change and urbanization will be exacerbating the public health challenges that Oropuche virus presents. So we wanted to look at if we could find any relationship between the seasonality of the virus infections and the midge biting activity. And we did this based on weekly incidents of human Oropuche virus infections that in Amazonas, Brazil. So to start off, we created an ordinary differential equation model, a dynamical system model with 8 different classes, sorry. And each class is either susceptible or infected. And we have different types of individuals. So we have animals, which are SA and IA classes, and those are slots in our case. We have SF and IF, which are forest midges, SH and IH, which are humans, SC and IC, which are city midges. And if you notice in our flow diagram, we actually have two separate cycles, like it was theorized by the biologists, that some of their infections will propagate in the forest or the sylvatic cycle, and the rest will propagate in the urban cycle. So the sloths and the forest midges are in the sylvatic cycle, the humans and the city midges are in the urban cycle, and humans actually link the two cycles when they go out to the forest to explore or living in a peri-urban environment. We assume that all of these populations, the sloths, the forest midges, city midges, and humans are constant in the time that we're looking at. So we were actually able to reduce the 8 equation model into just 4 equations. And those 4 equations are a lot easier to do some mathematical analysis on. So we did that. We found a disease-free equilibrium where all of the infected populations are at 0, meaning that the disease cannot propagate at all and dies out. And we also found an endemic equilibrium where those infected populations are non-zero, meaning that the disease is still circulating. We use the next generation operator method to find R naught. You may have heard of R naught during the COVID pandemic, and it's just a numerical representation of how many people can one infected individual infect. We also found an upper and lower bound for R naught, which is pretty useful in terms of trying to control how big R naught is. And we would like to control it in a public health intervention. We want R naught to be less than 1 so that the disease cannot propagate further. And that would mean the disease-free equilibrium is the scenario that we would end up in. Past the qualitative analysis, we actually modified our model to become non-autonomous, meaning that some parts of our model will depend on time, and those parts are actually the infection rates. So we changed our betas to be functions of time because this infection really occurs at its highest concentration during the rainy season in the Amazon. So we wanted to incorporate that somehow into our system of ODEs. And we did that by making our betas functions of time. And we've tried different functions. We use exponential functions, the beta function from statistics, and we're still working on trying to find the best one. We also did some parameter estimation, so more quantitative work. We found some parameters from literature, and then the rest we've estimated using a least squares optimization approach. In terms of numerical results, we were able to get okay fits, but not something we're super happy with yet. If you look at figure A, you can see in red the actual infected data, and then the blue curve is our simulated infected human population. And in figure B, it's the same, but it's cumulative instead of weekly. We were able to find less than 10% error in the cumulative case, but a lot higher in the weekly infection case. So we're still trying to figure that out and work on that more. So in terms of discussion and future work, Orpucci virus is becoming a major public health threat. Our math model is novel and it could be used to describe the dynamics of the virus. And we are able to compute the R naught, but we're still working on some quantitative results and incorporating seasonality into our model. So thanks for listening, and I hope to see y'all at Discover.